Welcome to this session on the Half Subtractor, one of the most important combinational circuits in digital electronics. In this session, we will understand how a half subtractor performs single-bit subtraction, explore its truth table, derive the logic expressions, and design the final logic circuit using the K-map method. So let's begin by understanding what a half subtractor actually is and how it works. A half subtractor is a basic combinational logic circuit. It is used to subtract one single-bit binary number from another. It has two inputs, A is called as minuend and B is called as subtrahend. It produces two outputs, difference, which is the result of a minus B, borrow, which is generated when A is smaller than B. The key points to remember are, it performs single-bit binary subtraction. Output has two bits, difference and borrow. Borrow indicates that A requires borrowing from the next higher bit. Half subtractor represents the simplest form of binary subtraction. It forms the basis for full subtractor and multi-bit subtractor circuits. Before we understand how the half subtractor works, let's quickly refresh the basic rules of binary subtraction. Binary subtraction involves only two digits, 0 and 1, and there are four possible cases. The first case is 0 minus 0, which gives a difference of 0 with no borrow. The second case is 1 minus 0, which gives a difference of 1 with no borrow. The third case is 1 minus 1, which gives a difference of 0 with no borrow. The most important case is 0 minus 1. Since we cannot subtract 1 from 0 directly, we borrow 1 from the next higher bit. After borrowing, the difference becomes 1 and the borrow output becomes 1. These four cases represent the complete behavior of single-bit subtraction, and the half subtractor is designed to produce these exact outputs using logic gates. Please remember, borrow occurs only when 0 is subtracted by 1. Now that we understand the rules of binary subtraction for single-bit values, let's build the truth table of the half subtractor. A half subtractor has two inputs, A and B, where A is the minuend and B is the subtrahend. It produces two outputs, difference and borrow. We now list all possible combinations of A and B. When A is 0 and B is 0, the result is 0, and no borrow is needed. When A is 0 and B is 1, we cannot subtract 1 from 0 directly, so we borrow 1 from the next higher bit. This makes the difference 1 and borrow 1. When A is 1 and B is 0, the difference is simply 1, and no borrow is needed, and when both A and B are 1, the difference becomes 0, and again no borrow is needed. This completes the truth table, showing all valid outcomes of one-bit subtraction. Before we derive the logic circuit, let's analyze the outputs using the truth table we just created. In a half subtractor, the difference output becomes 1 when the inputs A and B are different. That means it behaves similar to an XOR function where the output is 1 for A equal to 0 and B equal to 1, or A equal to 1 and B equal to 0. On the other hand, the borrow output becomes 1 only in one specific case, when A is 0 and B is 1. This is because we cannot subtract 1 from 0 without borrowing. By observing these patterns, we can now use the K-map method to simplify both the difference and borrow expressions. Now that the truth table is complete, let's derive the simplified Boolean expression for the difference output using a two-variable Carnot map. In the half subtractor, the difference output behaves very similarly to the sum output in the half adder. We place a 1 in the K-map wherever the difference column in the truth table is 1. From the truth table, when A is 0 and B is 1, the difference is 1. When A is 1 and B is 0, the difference is also 1. When we plot these values on the K-map, the two ones appear diagonally opposite each other. Since diagonal cells cannot be grouped, the expression cannot be simplified into a larger group, so the final minimized expression for the difference becomes A bar B plus A B bar. This is exactly the XOR function. Therefore, the difference output of the half subtractor is A XOR B. Now let's simplify the expression for the borrow output using a two-variable K-map. Just like before, we begin by placing the borrow values from the truth table into the K-map. Borrow becomes 1 in only one situation, when A is 0 and B is 1. This means we need to borrow from the next higher bit, because B is larger than A. When we fill the K-map, we see that the only cell containing a 1 is the one corresponding to A equals 0 and B equals 1. Since there are no adjacent ones, no grouping can be formed in the K-map, so the simplified expression directly becomes B and A bar. This matches the standard borrow formula for the half subtractor. Therefore, the borrow output of the half subtractor is b multiplied by a bar. Now that we have simplified both the difference and the borrow expressions using K-maps, we can construct the final logic circuit of the half subtractor. From the K-map simplification, we obtain two equations: difference equals a XOR b, borrow equals a bar dot b. This means the half subtractor uses two basic logic gates, an XOR gate to generate the difference, an AND gate, along with an inverter for A, to generate the borrow. Input A is passed through a NOT gate first, and then combined with B through an AND gate to produce the borrow output. Both gates receive the same inputs A and B, and together they form the complete half subtractor circuit. So the final logic diagram contains an inverter for A, an XOR gate for the difference, and an AND gate with A bar dot B for the borrow. With this, we have completely understood the half subtractor, its working, truth table, K-map simplification, and the final logic circuit. In the next video, we'll move one step ahead and learn how the full subtractor works. If you have any doubts or feedback, feel free to use the comments section. Your support and encouragement motivate us to bring more useful content. Please don't forget to like, share, and subscribe. Let's meet in the next video.